Okay, to finish off the conic sections, we're actually finishing with the easiest of the conics. This is a parabola, and I force it to lie on its side because we're so used to using the ones that face up. This is obviously not a function, but it's still considered a parabola. Alright, so the definition of a parabola, similar to the ellipses and the hyperbola, where the ellipse is the sum of the distance from the foci to a point on the graph, and the point on the graph to the directrix, this line that's imaginary off to this side in this case. For an ellipse, the sum of those is a constant. For a hyperbola, the difference of those is a constant. For the parabola, it's actually much easier. Their distances are exactly the same. So no matter where this point is along the graph, the distance from the foci to the point and the point to the directrix are equal. So that gives us a couple easy points to work with. For instance, if we're at the vertex of the parabola, then the distance from the origin to the foci and the origin to the directrix is equal. So if I can plot the foci, I can also find the equation of the directrix. Where the ellipse and the hyperbola were a little bit more ambiguous in how to find that. There is a way of doing it, but it's not very friendly. This one's very easy. So if you go to the vertex, the focus in this case is 2 units to the right. Then the directrix will be 2 units to the opposite direction, 2 units to the left. If the focus went up 2, then the directrix would go down 2, and so forth and so on. Another couple points of interest are when the two lines are perpendicular to each other. At that point, their distances are exactly the same. So this distance here is 4 units, so therefore it's also 4 units to the directrix. And this 4 becomes important because it's 2 times the distance between the origin and the focus. So you get 4 up, and down here you're going to get 4 down. And this line segment created by this gives us these 2 points. Here, let me move the P way here. This point here and this point here with line segment that goes the complete distance here. This has a fancy name. It's called the Latus Rectum. I wouldn't say fancy, it's a weird name. So this line segment from here to here, this is considered the Latus Rectum. Alright, and that makes graphing a parabola kind of easy. You find the focus, you find the directrix, and then you go 2 times the distance of the focus up and 2 times the distance of the focus down, and you have these 3 points that you can plot, and then draw your parabola through them as best as possible. So let's look at this idea of a parabola a little bit more algebraically. There we go. So let's start with the idea that these 2 distances from the foci to the point and the point back to the directrix are exactly equal. And what they're equal to becomes very apparent if you're down here, but it really doesn't matter. So let's give this point P the coordinates, make this smaller, xy. And let's make this point down here the coordinate c comma 0, because c is usually what we call a foci. But later we're going to call it little a rather than c. It's just a convention, no idea why they changed it from c to a, and it's a little a at that. So the distance from here to here is a, therefore the distance from here to here is also a, so this equation for the directrix is x equals negative a. Alright, so the idea here is that this coordinate up here is going to have a coordinate of negative a because it's on the directrix, and a y coordinate of y because that's how high this point is all the way across. Alright, so if I find the distance between these 2 points and set it equal to the distance between these 2 points, we should come up with the formula of the parabola. All right, so let's call this one D1. Let's call this one D2. So off the bat, we have D1 is equal to D2. The distance for D1 is going to be, let's see, change in x. So x minus a negative a, so that'll be x plus a. And then that'll be squared, plus y minus y, which will be 0. That's kind of nice. All right, D2 is going to be x minus a all squared, change in x's, plus the change in y. Here we're going to get y minus 0, which leaves us with just y squared. All right, so it's not as complex as the ellipse was when we went through it, and it definitely not as complex as the hyperbola, which we did not do. All right, so the nice thing here is they're both square roots, so I can just drop both of them or assume that I square both sides. Expanding this out, we're going to get x squared plus 2ax plus a squared. On the other side, we're going to get x squared minus 2ax plus a squared plus y squared. And then a few things are going to cancel out. So let's see, the x squares are going to cancel, and the a squares are going to cancel, because they're both on opposite sides. So if I shift over a few things, and I'm going to rewrite it in a different order, we're going to get y squared is equal to 4ax. So after a little manipulation, we get this. And this is the general setup of a parabola. And in this case, because it's y squared, it's a left-right parabola. If it was an x squared, it would be an up-down parabola like we're used to, a function. All right, and then this a here is the focus. So to find the focus, the value you have to move left or right in this case, is buried inside this coefficient of 4a. So an easy example, just to play around with, would be y squared is equal to 4x. So the technique then becomes take the coefficient and say, well, that's 4a has to equal that coefficient 4. So in this case, a has to equal 1. So when we graph a parabola with this, we know it's y squared, so it's going left or right. I'm just going to draw a sketch here. And we know that the focus is 1 to the right. It's positive 4x, so it's going to go 1 to the right. So this would be the 1, but it's also known as the focus. This is 1, 0, the focus. And the directrix is going to be 1 back, so we're going to get this imaginary line where every point from here to the graph back to the directrix has to be exactly the same. So that means the vertex has to be right there, because it's 1 unit and 1 more unit, therefore those two distances are the same. So our graph is going to have a vertex at the origin, and then the other points are going to come from this idea that the lattice rectum. Now if you remember right, when our focus was 2, we had to go 4 up and 4 down. There's an algebraic way to prove that. Here our focus is 1, so if I substitute in 1 for x, we're going to get y squared is equal to 4 times 1. Square root both sides, and we're going to get y is equal to plus or minus 2. So that means we need to go up 2 to the coordinate 1, 2, and then down 2 to the coordinate 1, negative 2. So we would go 2 up and 2 down, and these points also become part of the graph, and the distance between these 2 points right through the focus is called the lattice rectum, and therefore we get a parabola that looks like that. So it's not a hard idea, it's actually kind of easy. Let's talk a little bit more about the vertex, the focus, and the latus rectum, because all of those become important when graphing one of these parabola. So we have a y squared here, so that means that the graph is going to be going left or right. The a, when you set the coefficient of x equal to 4a, when you solve for a, that becomes our focus and directrix, depending on its sign. If it's positive, it'll go to the right. If it's negative, it'll go to the left. If it was x squared first, then if it's positive, it would go up, and if it's negative, it would go down for the vertex. And then the directrix would be its opposite direction. All right, so once we get a, we know two things. This thing was not transformed because it's just y squared and x, no parentheses and weird numbers around. So we're guaranteed to be able to plot the vertex first. After you plot the vertex, then you're going to decide on which way to move the a units. Let's assume that a here is positive. So we're going to move a units to the right for the foci. So this would be the coordinate a comma 0. So just from the equation, you generally can come up with these 2 points. It's the other points that you need to graph the parabola that are important. So that's where the latus rectum comes in. So knowing that this is the foci, we can say, well, let x equal a and see what happens. So we'll take our equation and substitute a in for x. So that leads us to y squared equals 4a squared. And if we square root both sides, we're going to get y equals plus or minus 2a. So what that implies is when x is equal to a, we're going to get a point on the graph of a 2a and another point on the graph a negative 2a. So basically, if we add the distances away from a, or the distance from 2a to negative 2a, when you find the distance between 2a and negative 2a, it'll always be equal to the coefficient in front of x, 4a. So the distance of the latus rectum was always the coefficient, in this case, of the unsquared term x. So to plot your latus rectum, you go directly up 2a units, and you plot a point, and you go directly straight down, in this case, down 2a. So you'd subtract 2a. And then you'd have 3 points to be able to draw your graph through. Let's jump right into a transformation type problem using the parabola. Now I know this is a parabola because only one of the variables is going to be squared. The other variable is linear. So here we're going to have a y squared x, so we know that this parabola is going to be facing left or right. Again, if it was x squared y, then this thing would be going up or down just like a regular parabolic function. All right. Now, the vertex is going to move according to these two numbers. And remember, inside parentheses, opposite direction. So this thing is going 2 up and 3 to the left. So 2 up, 3 left, and that'll give us the coordinate negative 3, 2. Remember, it's left or right is x, up and down is y. All right, so we need to put in some asymptotes, and I'm not going to put them in, well, maybe I will. I'll put them in dotted. It'll be kind of messy. So we're going to need a up 2. So one of our imaginary axes in this case is going to go this way. And the other one is going to go left 3, 1, 2, 3. So our parabola is moving to this new location according to these orange axes, translated axes. So our first point of our graph is going to be the intersection of them. So there is the vertex. All right. The second part of it is we take the coefficient of the x term. We don't want to distribute it out. It's going to just be the coefficient of the x term. And we know that that's going to equal 4a. So 4a is equal to negative 2. Therefore, a is equal to negative 1/2. So that means our vertex is going to go 1/2 away from the vertex. Now the direction it's going to go in is dependent on the sign. If it's positive, it's going to go right. Since it's negative, it's definitely going to go left. So we're going to move left 1/2, and this becomes our foci. So the coordinate of that foci is going to be negative 3/2, or 3.5, comma 2. Negative 7/2. All right, then the directrix has to go the other way. So the directrix, D, is going to equal, or be, the equation x equals. Now we need to take negative 3 and bring it back 1/2. So that's going to be negative 2.5. So the directrix would go here. Straight up and down. All right, now for the latus rectum. Now, the latus rectum is going to go 2a up and 2a down for a grand total of 4a. If you didn't notice that in the last one, when the foci was 2, you would go 2 up and 2 down, which would give you a distance of, I'm sorry, you'd go 4 up and 4 down for a distance of 8, which is 2 times 4. So this number 4a is always going to be the latus rectum. All right, so 2 times 1/2 is 1, so it's going to go 1 up and 1 down for a grand total of a distance of 2, and those become physical points on the graph. And the 2 is that number right there, so that's the latus rectum. And then we can draw our parabola just going through those points. And we get that. And that's all there is to graphing a parabola.